Howdy, everybody. This is our maintainer talk on the Operator Framework group. We are an incubating project under the CNCF. Please move. Okay, you do it. All right, my name is Jordan Keister. I am a maintainer for the Operator Lifecycle Manager and a committee chair. And I'm also a principal software engineer at Red Hat.
I'm Joe Lanford. I am a software engineer at Red Hat, and I've been working on the Operator Framework for 7 or 8 years now. Also a steering committee member for the Operator Framework CNCF project.
Hey everyone, I'm Rashmi Gottipati, and I'm on the same team as Jordan and Joe. And I'm a senior software engineer and one of the maintainers of the Operator Framework project.
Hi, I'm Attila Mészáros, maintainer of Java Operator SDK, member of steering committee and software engineering at Apple.
All right, so for those in the audience, because it's really hard for folks on the internet to show a hand, how many of you have not installed an operator on a cluster? Cool, this is good. All right, so how many of you then have heard about our OLM v1? Fantastic. Of those, who has tried it? Fantastic.
Oh,
okay, well, I'm still going to give some background, but I'm delighted. There we go. So quick background here, Operator Lifecycle Manager is a project aimed at the idea of providing automated lifecycle management for operators on a cluster. And we have over 380 operators in our catalog in Operator Hub IO, as well as a number of downloads on GitHub. Our notable milestone was to hit our 1.0 release on our OLM v1 product last December. And subsequent to that, we have 41,000 or so downloads on GitHub. Oh, wow. The slides are all messed up. Cool. So we're not going to do this as query response. Okay, cool. So we got a lot of feedback while we're incubating in our OLM v0 product. And we identified a number of pain points that our customers were having that unfortunately tended to resolve in some very fundamental architectural decisions that were made on the product. As a result, a full rewrite was necessary from the ground up, and that's been the project goal of our OLM v1 product, is to alleviate these pain points. So let's see. Big pain points here. Unintended upgrades. You make a change in one namespace, it occurs in another one. Oops. We solve this with isolated and deterministic installs and upgrades, v1. v0, automatic RBAC aggregation. What you see is not always what you get. The new one, explicit bundle scope permissions, every time. A challenging uninstallation, where there's things left behind. You're not quite sure on what you need to remove further. Solved with the deterministic and complete cleanup. Installation failure, diagnostics, and clarity, solved with fully declarative GitOps-friendly models. Lack of version pinning, where you could designate a version only for your initial install, but not for subsequent mobility. Solve that with complete control over the desired upgrade path. Opaque non-Kubernetes-like resources, like the install plan, for example. Kube-native resources, nothing hidden. Big one here, 9 user APIs to 3. Simplicity. All right, so that was the background on v0 to v1. Now we'll talk a little bit about what we've done since last December when we put out our 1.0 release. We have focused a lot on compatibility with existing operators and catalogs. So we have support for registry v1 bundles with webhooks, as well as single and own namespace install modes. We are working in the direction of a cluster extension revision API, which allows us to track our installs, upgrades, and manifest changes along the way, with additional monitoring built in. And additionally, experimental is some tooling we have around the idea of a kubectl operator plugin that allows you to manipulate OLM v1 resources on the cluster. All right, to give us more information, I'll pass it over to Rashmi.
Yeah, so let's talk about webhook support. So the backstory for this is when OLM v1 was released, it didn't have support for webhook definitions in the bundles. And that turned out to be a pretty huge gap because roughly 20% of bundles in the Operator Hub IO catalog contain webhook definitions. And on top of that, the lack of conversion webhook support could present upgrade barriers when an operator introduces breaking API change and as APIs keep evolving. What's changed now is that we've added full support in OLM v1 for registry v1 bundles to include webhook definitions, specifically in the bundle manifest cluster service version via the spec.webhook definitions field. And operators can now include validating, mutating, and conversion webhooks in their bundles, and OLM would install and manage them in a declarative manner. And also adding support for conversion webhooks lays the foundation for safe upgrades across breaking API changes. So there's another important shift here, which is that we have OLM v1 no longer tries to do certificate management itself. We are relying on third-party certificate management. So we are integrating with Cert Manager and OpenShift Service CA, which is a move away from OLM v0's custom certificate logic, and that kind of keeps us aligned with the broader Kubernetes ecosystem. So with this addition, bundle authors benefit because their bundles would now just work in OLM v1, and also cluster admins benefit because they would get safer upgrades without any manual intervention. Next, we have single namespace and own namespace installs. So a little bit of context for this. So OLM v0 had 4 install modes: single namespace, own namespace, multi-namespace, and all namespaces. And these install modes were an implementation detail of OLM v0 support for multi-tenancy, which is to install the same operator multiple times on a cluster. But in practice, that caused a lot of confusion and complexity around RBAC and cache behavior and so on. So stepping back and just talking about Kubernetes, Kubernetes itself is single tenant when it comes to API management. So CRDs are cluster scoped, not namespace scoped, and so every controller that owns the CRD effectively owns the API across the entire cluster. And namespace scoping across tenants can't truly isolate tenants in the way we expect it to. So OLM v0, when it tried to manage multiple tenants sharing the same global APIs, we ran into all sorts of problems like unintended upgrades and unintended CRD downgrades and so on. Not just that, but the way Kubernetes informers work, we had some performance concerns as well, because when you're watching all namespaces, when you're watching multiple namespaces but not all namespaces, the controller is basically forced to maintain separate caches and watches per namespace, which, as you can imagine, ends up spamming the Kube API server. So due to these reasons, in OLM v1, we made a deliberate decision to not support multi-tenancy and to embrace the single tenant model. So initially, only all namespaces were supported. But that caused a little bit of friction for operators that were built for OLM v0 and only had supported single namespace and own namespace installs. So for now, we've added limited support specifically for registry v1 bundles to include a single namespace and own namespace install modes. And the way we are surfacing this to the user is through the watch namespace attribute in spec.config. So this is kind of user configurable. And yeah, so the takeaway here is that we don't have any intentions to tip our toes back into multi-tenancy, but we just want the existing operators to work seamlessly in OLM v1 and to kind of provide that migration path to v1. Yep. Next, we have, last but not the least, we have the revision-based lifecycle management. We have a new revision-based API, which is called the cluster extension revision. So a little bit of context of OLM v0's install plan. We had something called as install plan, which was mutable. So the plan could kind of change mid-flight, and it's also opaque. It's hard to understand what would be applied to the cluster. And so it caused us a lot of of issues like unintended upgrades and downgrades and a lot of silent failures, basically. And it was also very hard to debug. So now we have come up with this new API, which is cluster extension revision, which essentially replaces the concept of install plan. And this becomes like a new unit of lifecycle in V1. So every time a user installs a cluster extension, a new immutable cluster extension revision gets created, and it basically captures the entire state of the installation bundle, metadata, manifest, and the configuration and everything. So basically, like a full snapshot of the state of the extension. And not just installation, but anytime there is configuration change or when a user wants to do an upgrade, a new immutable revision gets created, archiving the old revision. So that kind of maintains history and progression of revisions. And it's easy to understand where we are at a given point in time. And all of this makes rollbacks and rollouts predictable and deterministic. And with this revision API, we also have a phased apply and probe mechanism where we look for whether all the resources in a particular phase are completed and ready to go before moving on to the next phase. So it's just easy to kind of figure out what's being changed in the cluster, as opposed to blindly just applying the manifests and moving on, or just stamping out everything at once. So yeah, all of this simplifies debugging and rollback, so that you can think of this as, compare this to like replica sets, how they track deployments. And with revisions, you can compare revisions side by side and easily see like what has changed and if you need to roll back to a previous known good state. So overall, this is a huge shift to revision-based lifecycling that kind of simplifies how OLM manages state and the lifecycle of extensions. Yeah, so let's look at how all this ties together. So basically, the content author would create a catalog that contains a set of bundles and publishes them to a registry. And then we have the cluster admin that would create a cluster catalog, referencing the image, the catalog image that is on the registry, and operator controller would then discover the available operator packages in that catalog. So we have operator discovery, and then a user, when they go to create a cluster extension, that's when they're able to say, I want to create this operator package pinned to this version and with this configuration. So OLM would then create the extension and manages its lifecycle. And anytime there's a change to the extension, the new cluster extension revision would be created, and that's how the install, upgrade, and uninstall are managed. Yeah, with that, I'll hand it over to Joe, who's going to give us a live demo.
All right. Let's see if this all works. Okay, so I'll just start stepping through it. So I've got an experimental install of our latest release set up and ready to go. So first thing I can show you real quickly is what a cluster catalog looks like. We just say we want to source from a catalog image, and we tell it which image we want to source from. We're going to poll every minute, but that won't matter for this demo because it won't change. So we'll apply that. Next, that should pretty quickly get ready to go. So if I cluster catalogs, we are serving and ready to go. So next we can install a cluster extension. So here we say which namespace we want to install it in, demo operator. We're going to use the demo operator installer service account to give it permissions to do the install and manage it. We're going to source from a catalog, and we want to install a demo operator package at version 0.0.1. And we're going to give it, this is new, as Rashmi was talking about with single namespace, we're going to give it an inline configuration. We want it to watch the demo namespace. So we will apply that. And that should go pretty quick, I think. That's the catalog. So rollout is in progress. We can see our cluster extension revisions here as well. So now it says it's available, and our cluster extension succeeded. All right, great. One thing we want to show is the single namespace actually gets propagated. So this is a command that's just going to show the OLM target namespaces as you know and love from OLM v0, gets propagated into the deployment of the operator pod. Well, gets propagated into the spec of the pod template spec. And so you see that it's watching the demo namespace. Next, we're going to try to upgrade to v2 of this thing. So this is just going to change the version to 0.0.2. I expect this to break because 0.0.2 doesn't support a singular owned namespace install. And here we're still telling it to use that configuration. So if we apply that, you will see that we applied it. And if I go look at the cluster extension, now it's saying, something's wrong, configuration error, unknown field, watch namespace. So we need to fix that. But meanwhile, I should show you everything's still running from v0.0.1. So we haven't changed anything yet. So let's fix that. So I'll skip over the fix. It's just removing the config. We remove the config, and now we can look at it again. And now it's at 0.0.2. I changed, we'd already changed the version to 0.0.2. So we just removed the config. Now you'll see that there are multiple revisions. So the second revision is now available. The previous one is unknown. We're no longer tracking it. And to show you the support for webhooks, this is just really quickly going through the validating webhook configuration, mutating webhook configuration, and the CRD to show you that we've got the CAs being injected and the services being set up. So that's all there. So now let's try it out. We've got an invalid CR here for the CRD that was created. That says, sorry, spec.valid must be true. If I show you what that looks like, we said it's false. And if I show you this one, it's true. So let's try to apply the one that's fixed. That worked, great, okay. And then the last thing we can show you here is the conversion webhook. So at v1, which is what we created it at, you have spec with mutate and valid right in the root. Notice the mutation webhook ran, we have this new mutate field. If we look at it at v2, you'll notice that now conversion is running, we've added this new layer. So we basically can show that we've got all those webhooks plumbed through and actually working correctly. Another thing Rashmi mentioned was the ability to diff cluster extension revisions. So in the future, we're thinking about implementing policy based on other agents in the cluster being able to decide when to do an upgrade or what's allowed to do an upgrade. And so you can imagine these other agents, either humans or other controllers, being able to do diffs of the revisions and decide if something is okay. Another thing that's probably pretty interesting is the ownership tree. So in OLM v0, the ownership tree was not really present. Using the kubectl tree plugin here, and you can see at the root is the demo operator. It's owning both of the revisions. The first revision owns nothing anymore since everything was migrated to or upgraded to version 2. And then the second revision owns all of the actual underlying resources. So we can see all those there. And then another way to look at this is to just get all the resources that have a certain label that OLM adds. And again, same list essentially. And then the last thing here is what happens when we delete the cluster extension. So we've deleted the cluster extension and now nothing is left. So we've actually cleaned up everything. You don't have to worry about trying to find everything on the cluster. That's the demo. And I think I'm handing it off to Jordan or Rashmi.
Yeah, so let's look at some of the limitations of OLM v1. So as Joe just showed, when you uninstall a cluster extension, basically everything is deleted. We have a cascading delete mechanism, basically a standard Kubernetes thing where when cluster extension is deleted, all of its dependent resources are being tracked via owner references, and OLM v1 would delete all of the dependent resources of that extension, which is quite contrary to what happens in OLM v0, where CRDs and CRs are left behind. So basically in OLM v1, the way currently this is, it destroys all of the user workloads, which is obviously not ideal. So we're working on adoption and orphaning logic, which is in orphaning, when you delete the cluster extension, you can leave all of the dependent resources, and adoption where it lets the revision or a reinstalled extension take over all of the dependent resources. And another limitation is that we don't have operator conditions API in OLM v1. So we're thinking of a successor mechanism that would essentially replace operator conditions by lifecycle participation from the extension authors. I mean, what this looks like is still TBD, but to give you a flavor of things, there could be different personas like bundle author and the extension author and the extension itself. So if I am, as the user, creating a cluster extension, I want certain level of control over how and when the extension should be upgraded. But there could be a cluster level policy that says, okay, all of the extensions need to receive these many approvals before we can apply it to the cluster. So ideally, we need to come up with a mechanism that would allow for multiple approval paths, but also something that provides good user experience without creating any stalled upgrades.
Right. A few other areas where we're working in to improve the experience. The legacy graph mechanics that we use for registry v1 bundles remain an area of complexity and confusion for many of the operator authors. And so we're working in that space. We also need docs and tooling work to help improve our content creators on RAMP to allow them to self-publish all of the artifacts that we need to serve this use. And then we have some initial experimental tooling, but a long way to go for our catalog inspection on cluster tooling as well.
So the road ahead, we want to improve our registry v1 configuration ability. So we want to be able to essentially pull forward the subscription spec config from v0 into v1 so that you can configure the same things you used to be able to configure. We want to allow support for direct bundle installs so you don't have to build a catalog, push a catalog, get all the bundles in there. You should be able to just tell us what bundle you want to install and us install it. Still looking at Helm charts. We have a little bit of experimental support there, but still need more work there. As we've talked about already, the cluster extension revision might be something that will be useful for improving our policy-based approvals of upgrades. You can imagine something like wanting a controller that knows what time it is and only approves upgrades at a certain time. We want to make sure that our telemetry and events and logs and insights are all there to help improve the debuggability of OLM. And then last, but certainly not least, is migrating from v0 to v1. That's a thing that everyone has been asking us about, and I think that's an elephant in the room that we haven't really gotten to yet because we just need to make sure that OLM v1 is ready to go before we ask people to migrate. And as we've been, sort of all the things that we've been talking about are the challenges and the road ahead, we're really interested in having the community help us out, whether you're here or watching on YouTube later. Come join us. We've got an open community. We've got meetings in the open, and we'd love you to come and join. And with that, Attila.
Thank you very much. So something completely different now. Just a quick summary of Java Operator SDK for this year. We had a major version release in January with lots of changes. I think that went quite well. It was quite smooth transition. We just had some complaints regarding our dependency resource feature, which was there some concepts we had to do something more explicitly. And so in this year, we are releasing multiple minor versions, and just here are some cherry-picked issues. And but in this talk, I want to focus on some topic which still makes lots of confusion, and actually we are improving that in 5.1, 5.3, and yeah, but not in just in operator world, but in general. So yeah, but before we dig deep on that, a quick recap on some basics. So we have this resource version in Kubernetes resources, which is always increments if we change the resource. But the current Kubernetes guidelines says that you should never compare these numbers. You should just always check it's a string for equality. And but in practice, it's a monotonically increasing integer. So what are we going to talk about? It's a problem of storing allocated values, as is sometimes referenced in Kubernetes guidelines. If you basically create a resource that at the end has an ID. So it's typically this is for external APIs. You get a generated ID, and we had to store it somewhere to later address this resource. And we are putting it in the status, usually, of the custom resource. So the problem is that it's not guaranteed in the controllers that you will see this updated custom resource in the next reconciliation. So basically, there is no read after write consistency in terms of the cache, although Kubernetes API is strongly consistent. And why is that? So back to the basics, when you do informers, informer is the kind of a core component of each controller framework. It watches the resources of the Kubernetes API server and gets the resources. It's basically the Kubernetes API server propagates these resources back to the informers through a WebSocket. And when we're doing a reconciliation, we are always reading these resources from the cache. So it's easy to see that if you do an update to the custom resource, it's kind of eventually consistently we are getting pushed these resources back to the caches of the controllers. So it's kind of a well-known issue with Kubernetes caches, and so basically the eventual consistency. And the problem happens when there is an additional informer. So basically, if there is an informer that triggers the reconciliation after we did an update and did not yet receive the updated resource version in the cache, we won't see that status where we have the ID in the reconciliation. And that is a problem because then the reconciler logic doesn't know if we already created the resource, it might try to create it again. So basically how to solve this problem and how to have stronger guarantees for the reconciliations and the caches in controllers. So it's a fundamental question, and there are multiple ways to solve this. One is just basically you can pull the cache at the end of your reconciliation synchronously, so you make sure that in the next reconciliation is triggered, you will have it in the cache. There is also a possible way to solve it with expectation patterns. And what we did in Java Operator SDK, we optimized for throughput and put an additional cache on top of the informer's cache. So the solution here is that we have a temporal cache, and the trick is that we do an update to the resource, we then get that response, up-to-date resource from the response, and put it in the cache. So in the next reconciliation, if somebody triggers it, we can take a look on the temporal cache. If the resource is there, read it there. If it's not, then read it from the informer's cache. And this is all nice, except the question is when to remove these resources from the temporal cache. So that would be on the next event. So we can theoretically evict it on the next event when we receive it from the informer, and then we know that the cached resources so the informer's cache already has the most recent version. Well, unfortunately, this is not that simple. First of all, we are not able to compare these resource versions. So if somebody updates the resource, meanwhile, as a third party, it's basically we cannot tell if that update happened before or after our update in our API server. So we might receive an event that is actually, we will see a resource version which is not equals to ours from the updated, but we don't know if it's before or after our update. So to solve this, and this is also true for the polling solution, you have to do an update using optimistic locking. In that way, you make sure that no update happened before your update, so you always, the next event that you will receive will basically have more recent resource than in one in the cache. So you can easily just evict the cached resource from the next event, and doesn't matter what a resource version is that. So in Java Operator SDK 5.1, we just prepared for you some utils. We can use just the simple method, just to patch the resource, and we'll make sure all these guarantees happen there, and it will, all the resources that you update with these utils will be present on next reconciliation. And now the cherry on the cake is basically Kubernetes for next version will have comparable resource versions. That means nothing really changes in Kubernetes. They're just kind of a realization that mostly etcd, or in some rare cases, relational database backs Kubernetes. And we can use these numbers if we are able to parse it as integers. And that, with the updated basically guidelines, it gives us much more power. So having this, we can modify the framework for you, and basically nothing changing our APIs, maybe some additional utils methods will be there, that in the background, that will eliminate the need for this optimistic locking. And on top of that, it allows all kinds of optimizations for this next upcoming version. Like, for example, if you update a resource, your own resource or custom resource, that would normally trigger the reconciliation again. But that's something that you always want, or probably you don't want, because then let's say your own update, you don't want to basically recheck that later. So we can able to filter out those events which are coming from our own updates. So then that's way sparing lots of reconciliation cycles that you otherwise would have. So, and some others which are even more technical, so I stop there, but it really helps, and the framework will be just much more efficient seamlessly. Thank you very much.